Okay, this is the review for the third midterm. The topics on the midterm exam are week 8, energy equation, both in chemical and physical form, if you like. Dimensional analysis, including Buckingham pi, and pipe flow analysis. It does not include pipe networks, which is week 11. The topics actually on the scheduled exam conform pretty closely to those three topics. Energy equation is one of them in the physical form. Dimensional analysis using Buckingham pi to solve a problem of similitude and to scale something, an experiment, and straight pipe flow in one of the modalities. So this will be posted on the resource homepage, and so the individual components are just these three individual pieces. So first off, the energy equation. And so, as you know, the energy equation is the 1D energy equation anyway, is written along a streamline. It has an upstream, which is important to identify, and a downstream, which is important to identify. It always has to be in that mode. It can have energy put into the system as a pump or removed from the system as a turbine. And the velocities are always streamline velocities that are defined. The general equation, as you know, is Bernoulli's equation: elevation head plus pressure head plus velocity head at the upstream location, plus a pump head placed within the system. And this is equal to the downstream behavior, which is the elevation head, the pressure head downstream, and the velocity head downstream, and sum of head losses within the system. So typically this has to be written for the upstream portion, and so it's no different from Bernoulli in that. It has to define the downstream portion. And it's important to do that because the sign convention is one where the pump head is positive if it's a pump and negative if it's a turbine, removing energy from the system. And we can always relate the pump head to the power output from the system multiplied by the mass flow rate and gravitational acceleration. So this is just the same as mass flow rate is density times volume flow rate and gravity. So you always follow this sign convention, and it always goes from upstream to downstream. Likewise, head losses are always positive, irrespective of which way you're flowing, and are typically given by either something like a loss factor and v squared over 2g. And I suppose it's important to realize that this is the velocity in some part of the system, usually in a pipe. So it's not necessarily the input or the output or the input velocities. It's a velocity that's within the system and is defined. So it's important to keep that straight. If you use pipe flow equations, then this head loss is equal to a friction factor, a length over diameter ratio, and again the velocity inside the component, the pipe. And this is either recovered from a laminar friction factor, which is 64 over Re for a pipe. So this is laminar. And Reynolds number is velocity, diameter, density divided by viscosity. And if it's not laminar and it's not a circular pipe, then it's you use the Moody diagram. And actually we'll talk about this later because we'll talk about three of these things. This is the energy equation. We'll talk about pipe flow when we talk about the third component. Okay? So that's flow in pipes. Head losses in systems, the energy equation. If we look at Buckingham pi or dimensional analysis, then I suppose you have to remember a few things. We define things in terms of the number of dimensions, if you like, of mass, length and time, or it could be force, length and time, but we've tended to use mass. We define it in terms of the number of variables, and the number of pi groups is equal to n minus k. And so if you have all three of these in the system, then mass, length and time in the system, then you'd have 3. And depending on how many variables you have defining the system, if you have 5, then it's 5 minus 3, which is 2, say. And so that's relatively straightforward. And then the process is define the variables, in terms of the pi groups. And in the pi groups, you typically have a pi group is some function of, well, won't use those as terminologies, length, diameter, density, and velocity, say. And typically 3 of those will be defined for you as repeating variables, and then you'll swap out magnitudes of the non-repeating variables, which might be in this case length, and in my case and another one would be mu. And so this would be an example where there are indeed 5 terms and 3 mass, length and time included in all of them. So with that, you can just use Buckingham pi to be able to define, in this case, the pi terms, pi 1 and pi 2. And then if you want to apply similitude, we look for 3 main requirements. Geometric similitude, which just means that the length ratios in the model and the prototype are constant. We look for dynamic similitude, which means that the Reynolds numbers typically in the model and the prototype are the same, constant as well. And if that's the case, then we can look at kinematic similitude, which typically means that the Euler numbers are the same. But more importantly, what it means is that if these two are both met, then you can look at the forces that are applied on the structure, such as lift or drag, to be able to define those behaviors. And so these 3 components of similitude are quite important. Okay? So that's the first 2, dimensional analysis. And the third one is pipe flow, which is actually not so different from looking at this expression here. But if we look at pipe flow, then it's basically the same behavior as before. if we're looking at flow within a pipe that has some diameter attached to it, some flow velocity in the pipe, some roughness defined as a height on here, and a relative roughness, which is the ratio of these. We know that volumetric flow rate is just equal to the velocity times the area. And we can just use the same Bernoulli equation as before. I'll be pedantic and I'll write it out. Pump input into the system and equal to the downstream characteristics of elevation head, pressure head, velocity head, and the sum of losses. And as we said before, these losses are laminar or turbulent. In both cases, they're defined in terms of a friction factor, the length of the pipe divided by its diameter, and the velocity head within the pipe. Important, this is in the pipe, and that this would be the length of the pipe that we're interested in. And we know that when we look at these behaviors, we typically use a Moody chart to be able to reconcile response that gives us values for a Reynolds number, which is a velocity, a characteristic length, which is usually the diameter, and the density of the fluid divided through by the viscosity. And this friction factor, both of these are log scales, typically in Moody. If you need it in the test, you'll be given it, so you don't necessarily have to bring it along. And maybe some behaviors that we have that look a bit like maybe this. And in terms of demarking these different zones, this is laminar. This is turbulent. This is about 2000 in terms of Reynolds number. This relationship here for a pipe is that the friction factor is equal to 64 over the Reynolds number, with the Reynolds number defined as here. And these magnitudes here are for different magnitudes of relative roughness, and this is the locus for a smooth pipe. And so if you know your laminar, you can directly calculate the behavior from this using this, you calculate the head loss, for instance, just by using the appropriate value of the friction factor, where it's a function of velocity, and so you can calculate that directly. If you need to calculate flow velocities where you're in a range where you don't know the flow velocity, then what you have to do is calculate an initial guess. And then what you typically do is calculate would be to calculate first a velocity. Once you have a velocity, you can calculate a Reynolds number by knowing the velocity, the diameter of the pipe, density and viscosity of the fluid. If you know the Reynolds number, then you can certainly calculate a magnitude of, for a given friction factor, say, or a given roughness, you can calculate a magnitude of the appropriate friction factor. And if, for instance, it was in this region here, it'd be straightforward, because as you change Reynolds numbers, you don't change friction factors very much at all in the turbulent regime. And this would give you the ability now to calculate a revised velocity. And if the friction factor hadn't changed from your previous one, you'd actually recover the final velocity. If, for instance, you were somewhere on a regime that was different from that you're able to move along it, then you just have to repeat this cycle. Once you've calculated a velocity, check the Reynolds number, see if the Reynolds number has changed from the previous one, and then if it has, you have to calculate a new friction factor and then go through the selection like that. And that's probably about it. Okay. Happy hunting on the test. And if you need to, come and see me before the test and we can discuss anything we need to. Okay. Thanks very much. Good luck.